1. What is not necessary to create a geodynamo magnetic field? 3 of these are. So let's go through the other way. Is rotation necessary? Yes, rotation is absolutely necessary. Is convection necessary? Yes. What is convection?
Heated things rise to the surface.
Yep. Heated things float up, cooler things fall down. A solid surface? No. Conducting fluid? Yes. So for anything that has a magnetic field created like a geodynamo, they need to have these 3 things. Does the sun have a magnetic field? Yeah, so it must have these 3 things. Its conducting fluid is not the same as our conducting fluid, but it has to have a conducting fluid that's swirling around. So the correct answer here was C. What is unique about the moon's orbit? It's locked. Does the moon have its own moons? No, it does not.
Can the moon have its own moons?
It's possible, yeah. I mean, think about it. The Earth is orbiting the sun, and we have a moon. It's just a scale issue. It orbits 2 planets? No, I really hope nobody said that one. It has a highly eccentric orbit? No, it's reasonably close to circular. What was that?
Can it orbit 2 planets?
There are, physics would say yes. I'm not aware of anything that does that, unless you want to consider something like Pluto and Charon are, if there's something that orbits both of those. I don't know that there is anything that orbits both of them, though. Right, because there are 4 other moons. If one of them orbits both, well, then that would do it. I have to look into that now. I'm curious. Okay, which is not a stage in plant formation? Yeah, not raining. Flooding, what is flooding? It's not the result of raining. What's the result of? Yeah, magma, molten material. In the early stages of the planets, because of all of the heat produced in the compression, they would pretty much have been molten surfaces. Just like I was watching a video yesterday of a lava tube in Hawaii, and you see the molten magma just sloshing around. It looks like red water. That's what the entire surface of the Earth would have been like. Finally, suppose you see the moon rise at sunrise. What phase is the moon in? If it rises at sunrise, we can draw a picture and say, here's the Earth, here's the moon, and here's the sun, because the sun rises at sunrise. If the moon rises at sunrise, it's in the same direction. And so how much of the side of the Earth we see is lit up? Which side of the moon will be lit up, folks?
The dark side.
A comedian. The far side of the moon will be the side that's lit up. So what we will see will be just a completely dark moon. And what do you call that stage, that phase? New. Okay, any questions about the quiz? We understand all of this material? All right, then let's talk about a review of the moon's rotation, because we're going to look at this with the rotation of Mercury and Venus as well today. So the moon has a tidally locked rotation. You see where I got that word synchronous from, but it's not synchronous orbit. It's synchronous rotation. It's tidally locked. That means that the tidal forces, the difference in gravity being stronger when things are closer and weaker when things are farther, has resulted in the same side of the moon always facing the Earth. So if you look at this diagram, it has a little mound on the moon so that we can keep track of which side of the moon is the same side. And that same side is always facing the Earth. This came about because of the Earth's gravitational pull. Initially, the moon would have been rotating. Almost certainly, it would have been rotating the same direction the Earth is rotating. But because of the gravitational force, things that are closer pulled harder. It basically would get slowed down Just a tiny, tiny bit each orbit until eventually it locked in. We've already learned this, but we're going to use it for comparison. So now we're going to go to Mercury. We're starting at the closest to the sun now. Mercury, the innermost planet, not made of quicksilver Mercury, but named after Mercury the god. It has been explored first by Mariner 10 in the 1970s. And so up until just a few years ago, basically all the information we had about Mercury came from what Mariner 10 picked up in the 1970s, which meant that our knowledge about Mercury was not as sophisticated as it is today. In 2011, the Messenger spacecraft went into orbit around Mercury. It stayed Mercury for 4 years. Its mission ended in 2015. And of course, when you have a spacecraft out there collecting data, it's collecting data a lot faster than it can transmit it. So for instance, even today, we had Pluto, a flyby of Pluto, a year ago? And they're still just receiving new information. And then that information has to be processed. So in preparing for today's lecture, I was reading about Mercury, and I found an article, a little news blurb that was written on September 26 about an article that's published in the October issue of a journal about new findings of Mercury. In fact, I think it's on the next slide. They're still getting new information from what was discovered by that Messenger spacecraft. But what are things that we've known about Mercury for a long time? Well, one thing is, we know that it looks... Alvin, you missed another quiz, buddy.
Really?
Really?
I figured.
Sorry.
I'm sorry.
Yeah. There is some reason to that. So Mercury looks a lot like the moon. In fact, if we go back to the first picture here of Mercury, if you look at that, you'd be hard-pressed to say that's not the moon. You have to know, what the actual layout of the moon is, where the craters are and stuff, to differentiate between Mercury and the moon. Looks a lot the same. Mercury is a little darker. Recent discoveries from Messenger have indicated why. Mercury has a little carbon coating, and that carbon is pretty dark, and so that makes it a little bit darker and not as, harder to see that. Doesn't reflect as much. Do you remember the term that we use for planet, for anything in astronomy, that talks about how reflective they are? Somebody asked me if it was where the word albino came from.
Albedo?
The albedo, yeah. So its albedo is very low. I didn't look up the number for the albedo, sadly, so I can't give you its number offhand. But it has a darker surface because of that carbon coating. You see lots of craters. You can see craters on this picture here. The temperature on the surface is really hot to really cold. Why do you suppose it would get really hot on Mercury? It's pretty close to the sun. At its closest, I should have put a 0 there, 0.29 astronomical units away from the sun. So just a little bit closer than 1/3 of the distance between the Earth and the sun. At its farthest from the sun, it's 0.41 astronomical units. Now, if you think about that, that's a pretty big swing. That's a fairly eccentric orbit. So it has an eccentric orbit, but even at its farthest, it's much closer than the Earth, so it's going to get a lot more radiation from the sun, hence a lot of heating. So if it's so close to the sun and gets so hot, how can it possibly get so cold? It doesn't have an atmosphere. The atmosphere will lock energy in and distribute it so that your temperatures don't fluctuate as much. If you don't have any atmosphere, when the sun goes bye-bye, there is no hot anything above the ground, and the ground then just gives off its heat into space and cools off rapidly. And so it cools rapidly when the sun goes down, so that when the sun's down, the temperatures will drop to as low as 70 Kelvin. That's colder than liquid nitrogen. In fact, it's a lot colder than liquid nitrogen. If I remember right, liquid nitrogen's like, no, liquid nitrogen I think maybe 77 Kelvin, so it's just a little colder than liquid nitrogen. If I remember my numbers right. Suffice to say, cold. Could humans live there? What are some reasons humans could not live on Mercury? Too hot, too cold, no air. Those are all good, solid reasons we couldn't live there. Furthermore, you wouldn't have the ability to grow anything because, now if you were to build yourself a shielded, chamber where you have an air supply, the ground, if you're all away from the surface, you could still live there. It would be a very low acceleration of gravity, but you can live in a low acceleration of gravity. You can live in no acceleration of gravity. But it has those weather conditions of no air, too hot and too cold, that would make it not work for us. Surprisingly, they have found a little bit of ice in Mercury, just like they found on the moon. That is, in craters near the pole where you have permanent shadow, the crater is deep enough and situated right that it never sees sun. They have found some frozen water, some ice. There is no atmosphere because it gets so hot on the side that's being beaten on by the sun that it can't hold on to any gases. And it has a low mass, hence a low escape velocity. So, really can't hold on to anything even if it was cooler. Okay. First clicker question. Where on Mercury would you look for water ice? I know I just gave the answer by accident, but... Web ASTR. Turns out capitalization doesn't matter. I didn't know that. There we go. All right, so we had 0, 1, 7, 3. And the person who's going to explain their answer is, whoops, that's the wrong class. Don't know how his got in the wrong class.
Hey, it wasn't him. Yes, that's fine.
Timothy 1. He's one of my students from Southwestern. Latifah. Which one do you choose?
I choose D because when the sun goes down, it got really cold because there's no atmosphere, so it doesn't hold on to anything.
Okay. Now that makes sense as far as she went. It gets plenty cold when the sun goes down to form liquid, well, not just liquid water, but frozen water to form ice. The problem is, during the daytime, it can't hold on to it. And so during the daytime, it will melt, and then it'll evaporate, and then it will leave the planet completely. So there won't be water there when it gets cold to form the ice. So that's why that's an unlikely place. So the only place that's likely is in permanent shadow. So at some point it could have got some water, formed ice, and it never could leave. Yes?
The craters where the ice is must be pretty deep because even in shadow at 700 Kelvin, that is extremely hot. And
but
you think that the heat around it, even if it's in shadow, the heat around it would slowly melt.
It would have to travel through the rock. You don't have air to do the heating. So it'd have to travel through the rock.
Okay.
And so, over large distances, it takes a long time. Now, there still is a size parameter. If it was a crater that's only 2 meters. Well, it's going to get there. But yeah, so there is a size necessary, but the fact there's no atmosphere means it's not as big as you might think. Okay, back to what it looks like. Here's a picture comparing the moon and Mercury. Which one of these two pictures is the moon?
The blue one.
These pictures are both taken to be about the same phase. How would you describe this phase? Well, it's not a quarter because quarters are halves. So if it was first quarter, it would be like this part is what you would see. Did you say something, Max?
Yeah, it would be like a waxing gibbous, right?
Okay, so this would be a gibbous phase. I think that's how you spell gibbous. And in the northern hemisphere, if we saw the moon like that, it has the D shape, and so it would be waxing if we viewed it like that in the northern hemisphere. That is, viewed it below, straight above, and it looked like that. But if you were in the southern hemisphere and it looked like that, it'd be a waning gibbous. So we can't be specific. It has craters, just like there's craters on the moon. It has some craters on top of others, but fewer of the craters overlap. So that suggests, that it's a younger surface maybe, because the older it is, the more craters on top of craters you're going to get. It has smaller rims of the crater. That is, your crater goes like this. That height difference is smaller, and that's just a result of the lower gravity on Mercury. The higher gravity on Mercury, the lower gravity on the moon. The higher gravity means the stuff doesn't fly up as much. One of the really unique things about Mercury is the presence of these things they call lobate scarps. These scarps, or escarpments, if you prefer, are cliffs that are like more than 1 kilometer tall. So really tall cliffs. And those cliffs are believed to be the result of shrinkage. That is, Mercury was a bigger ball, and its core shrunk. And as it shrunk, you get more and more pressure pushing things until something breaks and it slides down. And so that's believed to be the cause of these lobate scarps. So now, what's the data here? What's the scientific data relating to this? Scientists observed what did I just say they observed? They observed these scarps. That's the data. Everything after that is a theory. It started out with somebody making a hypothesis. Well, what could make those? Well, it could occur if we had something cool, because we know when things cool, it contracts. So there's the scientific reasoning. When it cools, it contracts. And so then they look for other things that might indicate, if it's because it's cool, then let's look for other things that might occur with it cooling on the inside. I don't even know what those are. Right? It's not my specialty, right? It's not vaporizing material with a laser here. It's my specialty. But the data is we see the scarps. Everything after that is interpretation of the data and what it means. Now, one thing that the scientists do very carefully is they say, okay, let's make a computer model and see if that's what the physics says would happen if it cooled. And it is. And here's what I was talking about, an article in the October 2016, issue of Nature Geoscience reveals that Messenger found smaller scarps, right? Messenger was able to make much more detailed images of Mercury than we could make with what was the first one again? Mariner 10. And so they found smaller ones, and those smaller ones, the scientists conjecture, because they still exist, that must mean they're younger. And so if they're younger, that means that maybe it's still contracting. And so they're saying that the story we have, the picture that scientists have put together, is that Mercury has done a lot of cooling and maybe is still cooling down. And as it cools, it contracts. And it's actually the core where they think this is occurring. The metal core contracts, and then the crust fractures to shrink down because the core is shrinking. And so those scarps is a big part of our understanding of Mercury's interior. Another thing is magnetic field. I'm going to stay here because I want to talk about the magnetic field. Mercury was not known to have a planet-wide magnetic field when Mariner went to visit it. But with Messenger, we now know that it does have a magnetic field. So if it has a magnetic field, what does that tell you?
It has the. Sorry, that's
What do you say, Russell?
It has a molten core.
Okay, it has a molten core still. It's not completely frozen because before the visit of Messenger, scientists believed that the core hadn't been completely frozen by now because it's small. And when things are small, because of that relationship that the surface area is, proportional to radius squared, and the amount of heat contained is proportional to radius cubed. If they're small, they can cool quicker. And so the assumption was it should be frozen to the core. But now they find it has a very weak, but a planet-wide magnetic field, so it must have a molten core, must have convection, that's cooler on the outside, warmer on the inside, and must have, swirling rotation. So we can use that information about what makes a magnetic field for the Earth and apply it here and make some conclusions about the core. Now, the picture I'm going to show you in a little bit doesn't quite match that because traditional belief has always been that it was solid. So let's answer this question. What do the lobate scarps indicate about Mercury? Bueno. Okay. We had some last minute adjustments, and you all agree. So, Aldwin?
Well, you were saying it's because they're monitoring the scarps with the monitoring the scarps that they seem to be shrinking, and we're talking about how basically the core is still cooling or was cooling, and basically the outer crust was just cracking and shrinking as well.
Perfect. So,
I was listening.
yeah, I did say you weren't. Although the fact that you suddenly had to put on your computer, find your clicker might have suggested that.
But yeah, I was.
There are some interesting other features. This Caloris basin, I believe the picture on the right is the side of Mercury opposite Caloris basin. And scientists believe that the impact on Caloris basin was so immense, you can't really tell in that false color image that there is a big crater there. But they believe that crater, or the impact was so large that it caused a shock wave to go through Mercury, and when it got on the other side, it caused the other side to puff out and have a little crater on that side. It was not because of an impact there, but because of the wave coming across the other side. We see that on the sun a lot. When the sun has a coronal mass ejection, it will make or a flare. It will actually make a shock wave go through the sun, and it will make stuff come off the other side as well. So we see that occur a lot on the sun, the rebound shock wave going through. And so that's what they believe happened to create that there. So here's the picture that we have of Mercury. Does this look like the picture we saw for Earth? Okay, Yari said no. Can you give us why you shook your head no?
I don't know. Different. Like the Earth has a surface.
Okay, well, this does have a crust. The crust is, this region right here. What's the next surface after the crust on the Earth? Crust, then mantle. Well, this has a mantle. Here's the mantle, which you see the word there. Then we have, for the Earth, we have first the liquid core and then the solid core. This here is only showing one core, although the color varies a little bit. At least some of that has to be molten for it to have a planet-wide magnetic field. But something that's really uniquely different about this is that that core is really large compared to the size of the planet. The Earth's core is it's about half of the Earth's radius. The mantle is about the other half. Here, the mantle is a much smaller proportion of the size. So we have a difference there. So when scientists look at this, well, here's another thing. The density, that's the same as 5.4 grams per centimeter cubed. Now, the average density of the Earth is 5.5 grams per centimeter cubed. So that's very close to the average density of the Earth. And so you might say, that seems like a reasonable number. But it isn't. It isn't reasonable because the Earth has gravity compacting material. So one of the things that people will actually do is they will calculate an uncompacted density. And the uncompacted density of Earth is somewhere around 3.3 grams per centimeter cubed. It's the gravitational pull that compacts it to get the higher density. Well, Mercury, with its much smaller mass, its uncompacted density is higher. And so it has an unusually high density. That's actually why the picture shows a large core. Because we didn't measure where the core is. Scientists measured its gravity, they measured its size, and they calculated it must have a really large core to have that high density. So it's not a direct observation, it's an interpretation. But then you have a really big question. Why is Mercury different? Why does it have a disproportionately large core?
Maybe it was a bigger planet.
Maybe it was bigger. Any other ideas? Well, all theories have something in common with Russell's idea. All the theories are there must have been some crazy collisions that went on. One theory is that there may have been as many as 4 objects orbiting closer to the Sun than Venus initially, and then collisions occurred, and Mercury is the lone survivor. But a general belief is it must have had collisions that knocked off some of its mantle, giving it a bigger core and less mantle. Do we know that to be true? No, we don't. One thing I was reading, another recent discovery from Messenger's information that was discovered, is that they have material on the crust that is from a very rare type of meteorite. It would be an asteroidal meteorite, a very rare type found on Earth. And so the theory is maybe that collision had a big thing to do with how it got here. Something that...
What was it?
I can't remember exactly what kind of meteorite it was because it's very rare, so I didn't know it. Would have had to memorize it. So we have some very interesting things. Note that its magnetic field is weak and offset, similar to the Earth's. Right, the Earth's magnetic field does not have the south magnetic pole right at the North Pole. It's offset. Mercury's has the same kind of offset. So here are some pictures indicating ideas of how we got Mercury with such a disproportionately large core. Mercury, in the early stages, when it was differentiated, but still basically molten, gets hit by something. And if you notice here, that's a major impact, right? Mercury pretty much gets destroyed in this impact. It's a large object, something that is nearly the same size as Mercury. And so a lot of the material that was in the mantle just gets blown away because of all of that energy in the collision. So it's a hypothesis, it's a theory. It's not known, right? You shouldn't go out and say, we know this happened, but we think it's likely to have occurred. Now, its orbit is one of the very coolest things about Mercury. It's eccentric. We saw that it has, at its closest approach, a separation of just 0.29 astronomical units. But at its farthest distance, it's a separation of 0.41 astronomical units. So it's a pretty non-circular orbit. But there are some other cool things going on here that really I love. Notice once again we have a little nose so that we can keep track of the rotation. Starting from start to where I just finished putting the blue dot on, how many rotations has it completed? It's completed 1/2 of a rotation. It's completed 1/3 of an orbit, but 1/2 of a rotation. So you keep going. Here it's completed 1 rotation and 2/3 of an orbit. Gets back to where it started, and it's done 1.5 rotations. Now let's look at sunrise, sunset. If you're at the start position, what time of day is it? It's noon because the sun is overhead. You get to, let's just label these, you get to position 1. What time is it here? It's just slightly afternoon because the sun is just a little bit to the right. If you are standing there and you're where the blue dot is, the sun is just a little bit to the right of straight overhead. You go here, it's a little lower, a little lower, a little lower. Hey, 2, 3, 4. Here we get to 5 and the sun is setting, right? Because it's right on the horizon. And you don't have the atmosphere, so when it's on the horizon, it really is setting there. And actually, is it on the horizon? It's still a little above the horizon. Here, I guess, is the one that's really setting. And then you keep going, and you get to the bottom, and it's midnight. So in the time for one orbit, how many days have passed? You went from noon to sunset to midnight. How many days is that?
One day? 2 days?
From noon to midnight.
From noon to midnight?
That's half a day. So in the time that it does to do one complete orbit, you've actually only gone through half of a day. You have to do 2 complete orbits to get the full day in. Is that crazy? And of course, it's done 1.5 rotations in the time that it takes to do 1 orbit. Do 2 orbits, it does 3 rotations. So it does 3 rotations in the time for 2 orbits. Very bizarre, don't you think? There's another, so we call that a 3-to-2 orbital resonance because it's 3 rotations to 2 orbits. It takes 88 days to go around the sun. So its year is 88 days. If its year is 88 days, how long is its Mercury day? When I say 88 days, I mean 88 Earth days. How long is a Mercury day in Earth days?
What is it, 1.5?
Well, it takes 2 complete orbits to go through one day.
160 something? 170.
So it'd be 176 days. 176 Earth days, which is, pretty outstanding.
Just not very much.
Okay, one last thing. The sun actually undergoes retrograde motion in Mercury's sky. That is, I believe it's when you get down here when it's going the fastest because it's the closest. You'll have the sun. Look, it's noon. Oh, it's before noon. Oh, it's noon again. Would that not be bizarre? Because of its eccentric orbit, so that its rotation compared to its speed actually can give you that negative appearance for the motion of the sun. So, where in Mercury's orbit will you find the sun having retrograde motion? And notice I have A, B, and C marked in the figure in case the words perigee, which means the closest to the sun, and apogee, which means farthest to the sun, don't resonate with you. It logged you out, Hannah.
Again, I don't.
Russell? Don't have an answer from you or Alvin yet.
Sorry, I couldn't see.
Can I answer, Russell? Okay. So we had 9 that said perigee, and I'm just going to leave that. I'm not going to quiz you on that because I want to talk about Venus as well. Venus, as you may or may not know, is the female planet. Now, I know it's a little unbalanced to have 8 planets and 7 of them are male and 1 is female. But because of that, scientists have a convention of naming everything on Venus with a female name to try to balance the situation a little bit. There are 2 things on Venus that aren't female names. Mount Maxwell is one, and Montes Maxwell, and it's Regius Planum or something like that is the other one. Everything else is named with a female name. So Venus is the female planet, hence.
What do you mean the king's plane?
Excuse me?
The king's plane?
I've actually never thought about it, but that sounds about right. So the whole thing, men are from Mars and women are from Venus. Well, you can see in astronomy, they've tried to make that the way we understand it. The biggest thing about Venus that is interesting is its rotation. It rotates very, very slowly and backward. So it takes 243 Earth days to do a rotation, and it does it the opposite direction of its orbit. Now, we talked about tidal locking, how tidal locking has locked Mercury into this crazy 3-2 resonance. You can't blame a backward rotation on tidal locking, because tidal locking tries to slow things down. It doesn't reverse the direction. So its reverse motion can't be because of an interaction with the sun. It has to be something else. And so one theory is maybe there's no real reason for all of the planets to orbit the same direction. That's what the scientists kind of tossed that one out, because the whole theory on how the solar system formed with the big solar nebula and collapsing and everything rotating around the same direction means that they should all be rotating the same way. And so what conclusion, it's a really fairly obvious conclusion, do you think scientists can come up with?
Something hit it.
Something hit it. Because we know if we're right about the solar nebula theory, there should have been lots of collisions for everything. We look at something like Mercury and something like the moon, we see lots of craters because they haven't had slow surface evolution to erase them. So Venus must have had a major collision that made it turn backward. Now, I was just recently, actually, you guys know Ken Osborne. His wife is a Lutheran pastor, and she was doing a talk on how science and religion sometimes has opposition. And I brought up with her the idea of Hezekiah and the earth. I think with Hezekiah, didn't the sundial go backward 15 minutes or something like that? Well, 15 what? Pace?
So it's under degrees.
Okay. Well, you think about that. If the sundial goes back, with what we now understand about time and astronomy, what would have to happen for the sundial to go back? Yeah, the Earth has to suddenly stop its rotation and go the other direction for a little bit, and then restart. Well, if the Earth stopped its rotation, what would happen to you? You have what we call inertia, your mass. And Newton's first law of inertia says you're going to keep going.
So we're going to get flung to one direction.
And so, yeah, everybody would be dead if that were to happen.
Well, anyone that wasn't strapped down to the earth.
Well, no, anyone who was strapped down would be broken in pieces. It'd be kind of like Ron White talking about a guy lashing himself to a tree to show that he was tough and he could withstand a hurricane. Ron White says, it's not the speed of the wind, it's what the wind is blowing. When you get hit by a Volvo, it doesn't really matter how strong you are. Okay, so if you were tied down, you'd just be torn apart by what's tying you down. But then again, if you believe in a God who can make miracles happen, you have to believe that God could just take the entire Earth and, using Star Trek terminology, put on the inertial dampeners and make it rotate and then go on.
Oh my gosh, Superman.
Right.
If
If he's a God that can make miracles, he can make miracles. Not just a little bit, but a whole thing. But for Venus, it must have had a tremendously large impact. The surface of Venus is very, very hot. It is, well, it doesn't say here, but it will say later on. It's around, I think, 850 kelvins. Hot enough to melt lead, it will say on the slide when we get there. It has an atmosphere 100 times more massive than ours. Put another way, the atmospheric pressure is about 100 times bigger than ours. Because Mercury is very similar in size to the Earth. Its mass is close, its size is close. It's a little bit smaller. So, surface pressure there, just a little less than 100 times, 90 times. That means instead of having roughly 15 pounds per square inch pressing on you, you would have, let's just multiply by 100, 1,500 pounds per square inch pressing on you. You know what you would be in that pressure? Yeah, you'd be a little bug that got squashed. So once again, humans could not survive there because the atmosphere is so heavy. Its atmosphere also, it's 96.5% carbon dioxide. That's the Al Gore gas, right? That's the one that Al Gore talks about that humans can affect that causes a greenhouse effect. And we believe that Venus has a runaway greenhouse effect. That is, its greenhouse effect is so strong that it is just super, super hot. And how did it get that way? The theory is it never got cold enough for water to form on the surface. Water on our surface encapsulates the carbon dioxide and puts it into rocks. It never got cold enough for that to happen. The water stayed in the atmosphere, was eventually mostly lost. Notice that it has thick clouds of sulfuric acid. So even though it has a lot of atmosphere, that sulfuric acid wouldn't do you any good. Right? Not only would it eat your skin, it would eat your lungs. It has lightning, but they've never detected rain. I guess I have to stop here. It's time for our Sabbath preparations to begin. Yes, sir?
What would happen if you